Welcome back to module 2. We are continuing the classical quantum correspondence, and next what we are going to study is how many ways I can present quantum dynamics maintaining classical flavor in it, which means that I would like to know the trajectory, and if I am presenting trajectory, what does it mean by that trajectory in quantum dynamics. So we'll begin with Arrhenius theorem. Although wave function psi xt, an associated probability density distribution for a particle in position space at a given time is always global or delocalized in nature, one can very easily determine the average position of the particle at a given time from the normalized wave function using this expression, and this is called the expectation value. What does it mean? I will present it. The average position obtained using the average using this equation is called the expectation value of the position. In fact, for a given normalized wave function, the expectation value of a physical or dynamical quantity provides a way to compute the average of repeated experimental measurements. So, wave function, how do I get? So, from wave function I get the density, and I have mentioned that density has a distribution in position space. And what does it mean by this distribution? I have performed the experiment, let us say, and first experiment has given me a position x1, let us say here. Second experiment I have got position x2, which is here, let us say. Third experiment I have got x3, which is, let us say, here. So, this is x1, this is x2, this is x3, and like this way. And if we keep repeating, after let us say Avogadro number of times I have repeated the experiment. After repeating the experiment, all I am doing is trying to organize my data. I am just trying to find out how many counts I have for these positions. I will see that for x1 I have, let us say, 2 counts. For x2 I have, let us say, 10 counts, and for x3 let us say I have 100 counts, and x4 I can have x4, x5, so on. Everything are actually less than 100, because that is the maximum number of counts I have, and that is the meaning of the distribution function. That is the meaning it is carrying, the distribution function carrying the meaning. Now, after doing this experiment, I can also find out the average of that value. Average is going to be x1 plus x2 plus x3, all these positions divided by how many times I have repeated the experiment. Here I am considering Avogadro number of times I have repeated the experiments, that is why I am dividing by N. This is going to be the average value of the measurement, and that average value would be the expectation value in the distribution. So, this is nothing but, this can be calculated theoretically. So, this is theory and this is experiment. Average value of the repeated measurement is nothing but the expectation value which can be calculated theoretically from its wave function, if the normalized wave function is known. If I know the normalized wave function, then its average value can be obtained, average value of the position can be obtained. The expectation value of a position represents a point in position space. It is going to be a single value. Average value is going to be single value, because I am summing them and dividing by number of times I have done the experiment. So, average value is a single value point. Similarly, expectation value is actually a single value. So, if I have a single value at a particular time, then this particular value at t equals 0 I will get some value, at t equals t1 I will get some value, at t equals t2 I will get some value, this expectation value, and so on. So finally what I can do, if I plot x average value as a function of time, I will see a trajectory. Just like classical trajectory, I will be able to construct the trajectory, and that is the basic idea of this. And the what I have presented right now, it is based on postulate 3, another postulate of quantum mechanics, which shows that which states that if a quantum mechanical system is described by a normalized wave function psi xt, then the average value of an observable which can be observed experimentally, like position, momentum, they can be experimentally observed, that is why they are observables. Average value of an observable corresponding to the operator A is given by, so for every classical observable which can be experimentally observed, in quantum mechanics I get the operator, corresponding operator. I have to take that operator and I can measure the, I can determine the expectation value by this minus infinity to plus infinity. I am showing it one dimensional, that is why I am taking one dimension A dx. This integration I have to find out. And also similar way I can use a square, expectation value of the square of that operator, that is going to be psi star square of that operator psi dx. And finally variance of the measurement, you can say standard deviation of the measurement or variance of the measurement is given by this expression. This comes from postulate, one of the postulates of quantum mechanics. So if I use that postulate and try to find out the expectation value from the wave function is global, but expectation value would be single value at a particular time, then I can get its how that is moving, and that can give me classical flavor. And exactly what we have shown here, if I these red dots let us say presenting the expectation value at different time, then these points, if I connect these points in xt diagram, what I am seeing, this line is nothing but the trajectory, just like a classical trajectory. So I have some way to present quantum dynamics in terms of classical trajectory. if I consider the average of the distribution. So as pointed out earlier, the expectation value of the position, which is calculated from a global function, wave function, represents a point in position space. First question is, how does the expectation value of position change as a function of time? So what I would like to know, I am convinced right now, we are convinced that yes, it is possible to draw a trajectory for quantum dynamics, but question is how that's evolving as a function of time. Can I get an equation for that? And that's the task we are taking up. That equation is called the Arden-Space theorem. So Arden-Space theorem is showing how the expectation value will evolve as a function of time. So we will begin with taking the first derivative of this expectation value. It is total derivative, not partial derivative, because expectation value does not depend on space. So if I take this first derivative, then remember here this is total derivative, but I have to, inside the integrand, I have to use partial derivative, because wave function depends on both space and time. This is simple derivative product rule. We do not need to take first derivative of x because it is going to be 0. Now I have to use TDSE, because from TDSE I will be able to get the first derivatives, and TDSE can be written as I h cut partial derivative. I have removed the variables from psi for clarity, but psi is going to be function of space and time. I have just removed it for clarity here. So this is TDSE. I can rearrange a little bit. Like this, and I will take the complex conjugate also. Complex form of the TDSE, complex conjugate form of the TDSE, that is going to be equals minus 1 by I h cut h psi star. So this is, we are going to insert now. This is going to be here and this is going to be here. If I insert it, I will get this equation. Minus 1 by I h cut x psi dx plus minus infinity to plus infinity psi star x 1 by I h cut dx. That is the equation we get. We will continue it, and one thing we will introduce right now is called Hermitian operator. Hermitian operator, we will rigorously we will go over Hermitian operator again in this class in a different module. What is the property of Hermitian operator? What what is the matrix representation of Hermitian operator, all those things we'll be studying. But right now we'll just mention one thing, is the Hermitian operator. The property of an Hermitian operator is following. If I have, let's say, a function, and if I take the derivative, I have, let's say, two functions. One is this one. This form, we know that this operator is going to act on this function only. It is not going to act on this function. So it is more like we three are sitting together. On my right hand side one person, and on my left hand side one person is sitting, and I am just talking. I'm allowed to talk to only one person, let's say on the right hand side. So I can talk to him only. I cannot talk to the left hand person. This is called, that's the way the operator is working. And if the operator is working following that principle, then it is not an Hermitian operator. This part is not Hermitian operator. Hermitian operator can talk to both, basically. So if I am allowed to talk to both the right hand, the person sitting on my right hand side and the person sitting on my left hand side, if I can talk to both, then it is called Hermitian operator. So dx, only differential operator, is not Hermitian operator. If an operator is Hermitian, then it can act on right hand part, it can act on left hand part without any constraint. So and one more important point we'll remember, we'll discuss that in details later, that all quantum mechanically acceptable operators has to be Hermitian operator, which means that all quantum mechanically acceptable operators can talk to right hand person or left hand person, both. So H is an Hermitian operator, it is the Hamiltonian operator. Because it is Hermitian operator, we can write down minus infinity to plus infinity, this integration f star h g dx. This can be written as minus infinity to plus infinity g f star dx. They are equal. You can see that h is acting on g here, and here h is acting on f star, which was on this side. So which way it's acting, that that order doesn't matter, because it is Hermitian operator. Don't think that every mathematical operator is Hermitian operator. For an example, d dx is not an Hermitian operator. d dx only acts on the right hand side, what I have in the right hand side. So mathematically, that's why this operator cannot be accepted in quantum mechanics. We do not consider it in quantum mechanics. So all Hermitian operators should be able to act on both sides. So if it is so, we can rewrite this equation as follows. I can write down 1 by I h cut minus infinity to plus infinity h psi star x psi dx equals minus 1 by h cut minus infinity to plus infinity psi star h x psi dx. You see, I have now changed the position of Hermitian operator, and that is possible. This is the way Hermitian operator will work. And if it is so, then I can rewrite this as follows. One by I h cut minus infinity to plus infinity psi star x h psi dx minus infinity to plus infinity. So this part I have written here first, and then this part will be written here. And this part can be written as this. So in the end, I'll be able to write down psi star h. I should put the hat on the operator, Hamiltonian operator, x psi dx. This is nothing but 1 by I h cut minus infinity to plus infinity psi star, this is x h minus hx psi dx. This difference is called another concept we are going to. So these are pending topics. We are just using them. We will discuss it in details. Another topic is going to be commutator of two operators. It is written as AB minus BA. In the shorthand, it's written as within bracket AB with a comma. We use this comma sign to represent it. So this is called commutator of two operators. So if it is like that, so this part is nothing but x comma h commutator. I will just change it. I'll make it I by h cut. In that case, the sign will change. And I will have psi star hx minus xh so we have this form of the time derivative of the expectation value. We'll keep reducing it because h is Hamiltonian operator. We can write down as h cut square by 2m again time independent potential. So we can plug that in here, and particularly we are interested in knowing this part hx minus xh, commutator of Hamiltonian operator and position operator. So for that, what I need to do is that hx minus xh is nothing but psi equals minus h cut square by 2m plus v x psi minus x h cut square by 2m plus v psi. So we can write down this part. If we take the second derivative of this xi, that's exactly what we'll have. The second derivative of xi, that can be written as plus psi, which is nothing but x second derivative of psi plus d psi plus, so I'll be able to write down plus 2 first derivative. So this can be plugged in here and I'll be able to write down minus h cut square 2m then 2 minus h cut square by 2m into x plus v x psi plus, now this part I'll calculate, is going to be plus x h cut square 2m x second derivative minus v x psi. Remember, v is a multiplication operator. And any multiplication operator can be placed anywhere. It doesn't matter what is the order, and that's why you can write down. We see that these two will cancel out, and we get this is the form we get finally. Now, if we think of the momentum operator acting on psi, it is nothing but this complex derivative operator. So one can write down that this first derivative with respect to x is nothing but 1 by minus 1 by I h cut momentum operator acting on psi. Okay, this part also cancelling out. So finally I get minus h cut square by 2m to this. 2 is also can cancel out. So I can plug that in here. I get this commutator. Finally I get minus h cut square by m, then minus 1 by I h cut position operator acting on psi. This is nothing but minus I h cut by m position operator acting on psi. So now we'll insert this. So this one finally we are getting as minus I h cut by m position operator acting on psi. This is what we can insert here. So in the end I get the first derivative of the expectation value is nothing but I by h cut minus infinity to plus infinity psi star, then px psi dx, which is nothing but 1 by m minus infinity to plus infinity psi star px psi dx. This form is familiar form because I said that for any expectation value of an operator, if I have an operator and I want to find out the expectation value of that operator, I can get it by taking this integration psi star a psi dx. That's exactly what we are seeing here. So this is nothing but the expectation value of the momentum. So what we are seeing finally, this is the equation we are finally getting. This is Arrhenius theorem, and this equation shows that this equation is very familiar in classical mechanics. In classical mechanics, we often use Newton's equation of motion, which is nothing but mv is actually momentum in classical mechanics. In quantum mechanics, if we take the average of position and average of the momentum, we see the same form of equation of motion. So this equation shows that how the average position of the quantum particle will evolve as a function of time, and we see that average position is evolving or following classical trajectory. Next we will find out how the average momentum will change as a function of time, which is part of Arrhenius theorem. We will continue in the next session.